Alright, hey everyone, welcome back to the FMA Club Day 2. Today we're going to be talking about kinematics and dynamics. This recording won't be as prepared, I guess, as some of the other ones. This is mostly a little bit of a repeat of last year's Day 1 and Day 2, a little bit of both. And some of the problems are excluded, some of them aren't. I think I even added an extra new one in, I'm not sure. But this is kind of a last minute thing because I was on the edge of either whether I should just send in last year's kind of videos or if I should record a new one. So I'm deciding to record a new one just because I want to, and I feel like it'll cover the material a little bit more. It's just a lot better than trying to look through last year's and trying to find which problems were covered. But yeah, so today we're going to be talking about dynamics and kinematics. So just a little bit of review of last time. Last time I introduced the exam at the club. We talked a little bit about kinematics with the kinematic equations and projectile motion. And we also talked about some exclusive materials, so some of the exclusive equations, so the height, range, and time. We talked about dimensional analysis, some error propagation, and some little tips and tricks. So that's about it. So today we're first going to be talking about graph analysis, right? So this is like a little example of what we're going to be looking at. This is a really nice visual that I like. So we can see our position in time, our velocity in time, and our acceleration in time, right? Let's see if I can get this out. Yeah, nice. Okay, so, oh my god. So position, velocity, and acceleration, right? All of these are time graphs. So interpreting graphs, right? All of these are going to be based with time in our x-axis, right? I don't know why it's doing that. Time is in our x-axis. So this is the basic, probably like physics 1 interpretation of it, right? So we start from rest at position 0, and we have position, velocity, and acceleration. And these are related to each other in some form or way. So velocity is going to be equal to the slope of our position in the curve. So at any point in time, let's say like at this point over here, the slope of this point is going to be our velocity, right? And so, in a similar note, our acceleration is going to be equal to the slope of the velocity curve at this point, right? So, our slope here is going to be something, and that slope is going to be our acceleration, right? So, we can even just go here and here, right? So, let's say, let me go here and do some stuff. Yeah, okay, all right. So, I think it's this button, or no, this one. No, it's not that one. What button is it? There we go. It is this one. So let's say we have a graph. We have a graph that looks like this, right? And so remember, this side is going to be time, right? The x-axis is going to be time most of the time, right? And then on our y-axis, let's say we start out with like, I don't know, velocity or something, right? So if our velocity looks something like this, right? Let's say this is like a straight line. And let's say our equation is vt, right? Our velocity as a function of time is equal to 2t or something like that, right? So our acceleration, let's find a different color for this. Acceleration, right? Acceleration, well, I guess this would be like 2t plus 3 or something, right? So our acceleration, we're trying to find our acceleration at this point, right? At this point, our slope, our m, is going to be equal to 2, right? So our acceleration at that point is also going to be 2. And if we look along this entire line, we can see that our slope along this entire line at any point in time is going to be 2, right? At any point in time on this line, on this graph, our slope of our velocity is going to be 2. So our acceleration, we can say, no. That's my brush size. I don't want to modify my brush size. So we can say that at any point in time, our acceleration is going to be equal to 2, right? That's because at any point in time, that's our slope, right? Okay, hopefully that makes sense. And on the other hand, we can talk about this a little bit more in the future, but that's the relationship between position, velocity, and time, right? And I just revealed everything again. So that's kind of what we just talked about, this slope and slope, right? So if we go back here, we can see that like at any point in time on this position, let's just say like at this point in time, 5 seconds in, our slope is going to be around like 13, right? That's our velocity, right? And so at this point in time, our slope at this 5 seconds in, right? At our time equals 5 seconds, our slope is going to be around like negative 1.5, right? And so that would be our acceleration at that point, right? Okay, so hopefully that makes sense. The next part is going to be more physics-y, right? So this is where the derivatives and the antiderivatives come in. And I don't want to overcomplicate too many things, so we're just going to talk about two things. First is power rule for derivatives, and secondly is the easiest way to solve for the antiderivative, right? All right, let's go straight to it. So let's say we have some kind of graph, right? We have this graph. We don't even have to do this as like, oh shoot, what have I done? What have I done? What have I done? What have I done? Okay, that still is there. That's me. Okay, so now that we're here, right? No. Okay, so now that we're here, let's just keep it velocity and time, right? So we just established, right? If we have all right, I'm just gonna pretend everything's okay. So let's say we have this equation, right? This graph, v of t is equal to 2t plus 3, right? That's what we just said before. So we stated that our acceleration for here is going to be equal to 2, right? So that was based on the fact that at any point in time on this graph, at this point in time, the slope is equal to 2, right? At this point in time, our slope is equal to 2, right? So that means that our acceleration, which is a function of the slope at any point in time, is going to be equal to 2, right? So let's just write this on the side. So when our velocity as a function of time is equal to 2t plus 3, our acceleration is going to be equal to 2, right? Okay, we have that established. Let's erase this. Oh no, all right. So next, what if we have something like this? V of t is equal to, I don't know, like 10 or something, right? There's no slope. The slope is 0, right? It's not changing at all. So our acceleration is going to be 0, right? Okay, final thing. I'm not going to write this on the side because that was kind of easy. So let's say our velocity looks something like this, right? Our velocity looks something like this, where let's say this is vt is equal to v squared plus 2. Okay, so our acceleration at any point, I'm just going to say it, is going to be equal to, oh no, this is supposed to be t squared. T squared. So this is going to be equal to 2t. What? 2t? How does that make sense? So this is where we get into something known as the power rule. So the power rule states that if I have something like x to the n, the derivative of x to the n, which is dvdt, right? This is dvdt. That's our acceleration. No, I don't want to do this. ddt, right? Okay, so our derivative of x to the power of n, which is to say the function of the slope at any point in time, right? The slope of this at any point in time is going to be equal to n times x to the power of n minus 1. So if I had, let's say for example, why did I do that in blue? I should have done that in purple. So x to the n is equal to n times x to the power of n minus 1, right? So let's provide an example. If my equation was x cubed, that would mean that our derivative of x cubed, this is just saying the derivative of, right? So the derivative of x cubed with respect to x is going to be equal to 3x squared, right? Because we have, this is n, right? 3 equals n, or n equals 3, right? N equals 3. So we have 3 times x to the power of 3 minus 1, right? Which is equal to 3x squared. So the derivative of x cubed is 3x squared. Now we can do that for some other numbers. So let's say we have 2x squared, right? N equals 2. The derivative of this is going to be equal to 4, right? This is 2 times 2. 2 times 2. x to the power of 2 minus 1. So this is going to be equal to 4x, right? All right, final one. Let's say we have something like 2x, right? Where n equals 1, right? 2x to the first power, so n equals 1. The derivative of this is going to be equal to 2 times 1 times x to the power of 1 minus 1. Now, x to the power of 1 minus 1 is equal to x to the power of 0. And we know that the power of anything to the power of 0 is going to be equal to 1, right? So we can just say this is 2 times 1. So the derivative of 2x equals 2. That makes it seem right. The derivative of 2x is equal to 2, which, as we proved before, is right? Because this is our slope. So 2x, the derivative of that, the slope of 2x at any point in time is equal to 2, right? So that's how we get that. And just a little bit of a clarification. 2x to the power of 0, this is just going to say 2x to the power of 0. How should I put this? Yeah, so 2x to the power of 0, right? So that's just saying 2. When we plug in 2 dx, right, this is equal to 2 times x to the power of 0, which is equal to 2 times 0 times x to the power of 0 minus 1. Now, we have a times 0, right? So that just means that this is going to be equal to 0. And that also makes sense, right? If we have something like this, if we have a straight line that's constant, the slope is 0 at any point in time, right? So the derivative of 2, the slope at any point in time of a function where y equals 2 or v equals 2 is going to be equal to 0, right? Alright, so that's a lot of explanation. Now on to antiderivatives. Now if we say that the power rule, the derivative of x to the power of n is equal to n times x to the power of n minus 1, then for the antiderivative, the opposite of a derivative, we're going to get 1 over n plus 1 times x to the power of n plus 1. That looks weird. What's going on? So let's say that this inside here is, I don't know, 3x squared, right? So the antiderivative of this would be 3 times 1 divided by 2 plus 1, remember n equals 2 here, times x to the power of 2 plus 1, right? So this is going to be equal to 3 times 1 over 3 times x cubed. These are going to cancel out. The antiderivative of 3x squared is x cubed. And we can, and remember, if you remember, the derivative of x cubed is 3x squared, right? So, antiderivative. It's the opposite of a derivative. One more thing about antiderivatives. Let's go back all the way here, right? Let's go here, and let's say we have a graph that looks like this. And let's say this is our velocity, right? And this is our time again, right? Time. So, let's say we have some kind of graph that looks like this, right? And this is going to be a problem on the thing, actually. So, our antiderivative can also be said as the area under the graph. So, if I were asking for the antiderivative between this point and this point, I would need to find the area under here, right? And that would be the equivalent of our antiderivative for that, from here to, let's say this is A and B. This area would be equal to the antiderivative from A to B of this vt dt, right? This area is equal to the antiderivative. That's all I'm trying to say here, right? Okay, hopefully that makes sense. That's going to be the derivative and the antiderivative stuff, right? And I'm going to go back here. Okay, so hopefully that makes sense. So that's how we also get the kinematics equations. So if we have our position y equals y naught, that's a constant, plus v naught times t plus 1 over 2 at squared. The derivative of that, remember, we're doing it with respect to time. This is a constant, so this becomes 0. V naught of t is going to be eliminated, right? V naught t. The slope is going to be v naught, right? So we're going to have v naught plus this 1 over 2 at squared. Remember power rule, so 2 times 1 over 2, that's going to cancel, times a, times t to the power of 2 minus 1, which is equal to t, right? So we're going to get v naught plus at. And that's exactly what we get for our velocity, right? And for acceleration, that's going to be the derivative of this. This is a constant, and t, the slope of at, is going to be a, right? So that's how we get that. We have this constant acceleration, right? Hopefully that makes sense. If that doesn't, just pester me in the comments. But that's going to be the little calculus that we might need to know. We don't even need to know, it's just helpful to know. All right, moving on. Here we're going to talk about relative motion, right? So the common problem is going to be a boat in a river. So let's say we have a river, and then we have a boat. The boat will move in this direction, right? Let's say we have this boat, and it moves at, like, I don't know, 3 meters per second in this direction, right? And then we have the river, which has a current, which means that it's going to be, the current is, I don't know, like 4 meters per second this direction, right? So the actual velocity of the boat, remember that velocity isn't going to be constant, right? So, well, no, it's not. So velocity is going to be speed with a direction, right? So that means that when we have two speeds in different directions, the velocity is going to be some amount of those two speeds together, right? So what I'm trying to say is, like, let's say we have two speeds, right? Let's say we have one speed in this direction and we have another speed in this direction, right? The total velocity of these two combined together, this is vector addition. Vector addition. You can look this up in your free time. But the total magnitude, the total amount of velocity and the direction is going to be this, right? It's going to be kind of like a triangle thing. So we can say this is like a, b, and this is going to be a squared plus b squared square root, right? This is a Pythagorean theorem, assuming that we have a right angle here, right? Or we can just say this is c, right? Hopefully that makes a little bit of sense. So that's kind of what relative motion is going to be. What I'm trying to say here is, like, let's say we have let's just go back to the river and the boat. Sorry. So we have a boat, and it'll typically, if there's no current, it'll move in this direction at like 3 meters per second, right? And then we have the current, which is going to move in this direction at 4 meters per second, right? So saying that these are right, we're assuming this is a right angle. So the total speed is going to be, remember Pythagorean theorem and Pythagorean triplets. So this is going to be the boat in the end, in the current, is going to move at 5 meters per second in this direction, right? So that was a lot of words. We're going to have an example in a moment, right? Okay, next we have dynamics. So this is not going to be like an in-depth introduction of dynamics. It's just kind of going to glaze over, and the rest of the slideshows and the rest of the material for the club might be a little bit vague at some points. Sometimes it's going to be like assuming that you already know some of this stuff. So if you don't, let me know. I'll try and change it up and explain a little bit more. So first of all, we know that Newton's second law is going to be equal, force is equal to mass times acceleration. That's the name of the exam. We know that if we have a larger mass, we're going to need more force for the same amount of acceleration. Or if we have if we want more acceleration, if we have the same amount of force and we have a lower mass, then we're going to have the same amount of then we're going to have more acceleration. Or if we have more mass, then we're going to have less acceleration for the same amount of force. That's what this is saying, right? Force is equal to mass times acceleration. There's a relationship between these. So what are some different types of forces that we need to know? The first one is the normal force. So this is going to be perpendicular to our contact surface. And typically a way of saying this is it's going to prevent the whatever the object is from just crumpling on itself, right? Tension is going to be along the string. So if I have some kind of string, oh, I just revealed everything. If I have, is that the right color? This is. So if I have some kind of object on the end of a string, if this has some kind of like gravitational force, there's going to be a tension force that counters it, right? All right, so next we have friction. So that's always going to oppose the moving direction, right? So if we have an object, we know what friction is, right? So if I have an object and we say it's on like wheels or something, right? As we move, there's going to be some sort of friction pulling it back, right? We're going to denote that as like this, and let's just say there's a force, right? Nothing's going to move on for the rest of our life, right? If I like move a block along a table, at some point it's going to stop unless I have a frictionless table. So that's what our friction force is going to be. And finally, we have gravity. So that's always going to be vertically downward in a dynamics problem. We're going to learn a little bit more about gravitation in the future, but for now, that's all you need to know. It's always vertically downward. So, final thing, I don't think I actually have a question on the worksheet that's about scales, but remember that the measured forces by scales is going to be the normal force on the measuring device. So I'm going to actually do an example of this, just because I don't think I actually have one on here. So let's say we have some sort of scale. Let's say the scale is, I don't know, like 5 kilograms or something, right? The scale is 5 kilograms, and when we place it on the ground, it's normal, right? So it immediately displays that it has 0 kilograms, right? Let's say we lift this scale up, holding it with 2 hands, right? One hand is supporting it. Let's say we have like one hand here. And then we have another hand that's pushing down with 225 newtons of force. So what is going to be, or 250 newtons of force, right? So what is going to be the reading on this scale? So first thing is, we know that this scale is 5 kilograms, and when it's on the ground, it's going to measure the normal force, right? There's a normal force of 50 newtons. Remember that 1 newton, our gravitational force. Let's do this better. So when our scale is on the ground, wow, this is a terrible scale. When our scale is on the ground, right? When our scale is on the ground, I want a brush. When our scale is on the ground, we have 2 forces acting on it, right? We have our gravitational force, which is equal to mg, right? So this is going to be equal to 5. That's the weight of this, right? This is 5 kilograms. 5 times 10, which is equal to 50 newtons, right? In the other direction, we have our normal force. And our normal force has to completely counteract this gravitational force. So this is going to be equal to 50 newtons as well. However, the scale's calibrated to say that there's 0 kilograms, right? There's nothing on the scale, so it's going to say 0 kilograms. So that means we're always going to be subtracting 50 newtons, right? Because that's our weight. So let's say we lift this up, right? We lift this scale up, and now we have 200 newtons, 250 newtons of force pressing down on this scale, right? Now 250 newtons pressing down on the scale, and we're going to subtract, and we also have another hand supporting it, right? So that means that we have 250 newtons of force on the scale, right? But we're also going to have to subtract that 50 newtons, so because of the calibration. So in the end, we're going to get a reading of, I think, 20 kilograms, right? So it's always going to measure the normal force, right? It's always going to measure the normal force. Did I do this right? I think I did this right. Yeah, because normal force, we have an external force that's 250 newtons, so that means our normal force is going to be 250 newtons. And then we subtract 50 newtons because of that calibration thing, and that means that we get a reading of 200 newtons or 20 kilograms. Hopefully I'm right. Hopefully that's right. If it's not, then I'm gonna probably unlist this video. Alright, so that's our little optional problem. I'm revealing everything again. Why do I keep on doing that? Alright, so back to here. Next, we're going to have circular motion, right? So this is motion when we're going in a circle. So I'm not going to go over this too much since we have an entire day dedicated to this in the future, but this is our tangential velocity, right? This is our velocity tangent to this circle, this motion, right? And then we have our centripetal acceleration. This is a good equation to memorize, which is v squared divided by r, and that's always going to be pointed inwards, right? We're always going to be pointed inwards when we're talking about centripetal acceleration. We can also have a tangential acceleration if we're going faster, but that doesn't always apply, right? And we're going to talk about some of these symbols a little bit more in the future. Alright, so that's circular motion. Next we have inclined planes. Now this is a big thing. So when we're on an inclined plane, I'm going to go back here. Let's say we have a box. No. Let's say we have a box on an incline. Oh, God. Okay. Let's say we have a box on an inclined plane, right? We have a box on an inclined plane. Now, there's going to be a few forces that apply to this box, right? Let's say this box has a mass of m. First force, of course, is going to be gravity, right? That's going to come from our center of mass. And this force of gravity is going to be equal to mg. Now, we can actually split this gravitational force into two components. We can do one that's vertical relative to this surface, and we can do one that's horizontal relative to this surface, right? So relative to this surface, this force is going to be mg sine theta, and we're going to have mg cosine theta, right? And by vector addition, these combine together to create mg, right? Okay, hopefully that makes sense. And another way to put it is like we can put this arrow over here, and that's going to, and this isn't depicted correctly, but it would look something like this, and the total would be mg, right? Okay, so we have mg cosine theta and mg sine theta. So why are we trying to split this? So the first thing is our normal force, remember, that's going to be perpendicular to our surface, right? Our normal force is going to counteract whatever is opposite of it. And whatever is opposite of it isn't mg, it's mg cosine theta. So our normal force is going to be equal to mg cosine theta. Next, we're going to have our friction force, right? That's going to be the opposite of our direction of motion, or whatever our direction of motion would be if it starts moving. So our friction force, this equation is going to be mu n, where mu is our frictional coefficient. We can have mu s, which is for static friction. That's when this block is not moving. We can have mu k when our block is moving. And that's going to be our kinetic friction, right? So this n is going to be our normal force. And typically, we can say that our mu s, when our block isn't moving, is going to be equal to tangent of theta. Now, why is it tangent of theta? That's going to be because of our normal force, right? Our normal force is equal to mg cosine theta. Our normal force is going to be equal to mg cosine theta. And so that means, and our friction force is going to have to directly counteract this force moving down, right? So we can say mg sine theta is equal to mu mg cosine theta. So we can cross these out. Sine divided by cosine is tangent theta. So that's why we get mu s is equal to tangent theta. Right? Okay, so that's a box on an inclined plane. You're going to be seeing a lot of problems referring to this. Alright, I think that's it for the slideshow. So we're just going to move to the worksheet. So let's zoom this in a little bit. So first, we have a graph problem, right? This is a graphical analysis. So the representation of the motion of a squirrel as it runs on a straight line along a telephone wire. Letters A through E refer to the indicated times, right? If the graph is a graph of position versus time, then the squirrel has the greatest speed at what time or during what time intervals. Okay, so greatest speed at what time? So this is a position versus time graph, right? So we're trying to find the greatest speed. So the thing about the greatest speed is going to be the absolute value. Let's put this in purple. So speed is the magnitude of velocity. So remember, velocity is speed with a direction. So I could say our speed is 5 miles per hour, right? Now, with velocity, I could say it's 5 miles per hour in this direction. I can say it's 5 miles per hour in this direction. I could say it's 5 miles per hour directed straight towards me or something like that, right? That's some chemistry fun. Anyways, I could say that it's like pointing directly towards me, right? I could say it's directly like away from me or something like that, right? All of it is going to be 5 miles per hour, and the speed is always going to be 5 miles per hour, right? No matter if I'm moving in the positive direction in 5 miles per hour, if I'm moving in the negative direction of 5 miles per hour, our speed is always going to be 5 miles per hour. Another way of saying this is our speed, we can denote that as s, is equal to the absolute value of velocity, right? no matter if it's negative or positive, it's always going to be 5 miles per hour. And I guess there's other ways of doing it, but you know. Okay, so we've established that. Let's do our little graph. So speed is the magnitude of velocity. We've already established that, right? Okay, let's do this and this, right? And we have graph that looks something like this, and then we have this, and then we have this, right? I think. Is that our graph? That's our graph. It's close enough. Okay, so we have points A, B, C, D, and E, right? Now, first, we're assuming this is position over time, right? So, our position over time, that means that the greatest speed at any point, or the greatest speed is going to be the greatest velocity, right? And remember, velocity is our derivative of our speed, right? So that's going to be the slope. So what part has the greatest slope? And it doesn't matter if it's positive or negative, it's just the greatest slope. And that's going to be between B and D, right? This has the greatest slope. This has the greatest slope. It has the sharpest slope. Even though it's negative, it's going to be the greatest speed, right? Okay. Next, if instead the graph, so that's going to be between B and D, so that's going to give us C, right? So if instead the graph is a graph of velocity versus time, then what point does it have the greatest speed? So this is going to be a little bit tricky. Remember, speed is going to be, once again, our magnitude of our velocity, right? And since this is just plotted by velocity, we can say that this is like 1 mile per hour. This is 2 miles per hour at this point, right? That's going to be our speed. So the points where there's the greatest speed is going to be the points of change, right? It's going to be the highest and the lowest point. So that's going to be B and D, and that's going to give us answer choice D, right? Finally, if instead the graph is a graph of acceleration versus time, and the squirrel starts from rest, then the squirrel has the greatest speed at what time during what time interval? So remember that our acceleration is the derivative of our velocity. So if we're going to find the greatest speed, we're going to have to take the antiderivative of acceleration and find the point where the velocity is the greatest. So remember that the antiderivative of something can just be the area under the graph, right? And remember, negatives are negatives. So if I have like up to D, this is going to be from A through C minus from C through D, right? So our greatest speed is going to be right before we hit the negatives, right before we start subtracting, right? So at point C, we're going to have our greatest speed. So we're going to have answer choice B for this. Next, we have a relative motion problem. So a 600 meter wide river flows directly south at 4 meters per second. Oh shoot, I have this in the wrong thing. Okay, so a 600 meter wide river flows directly south at 4 meters per second. A small motorboat travels at 5 meters per second in still water and points in such a direction that it will travel directly east relative to the land. This is 600 meters. The time it takes to cross the river is closest to this, right? Okay, let's go here and here. I hate having one screen only. So we have a boat. We have two. We have a river, right? This is 600 meters. Our current is flowing 4 meters per second. 4 miles per hour. What is it? 4 meters. 4 meters per second. I was right. Wow, that's fast. Okay, so 4 meters per second in this direction, and we have a boat that moves in this direction at 5 meters per second, right? And we have it in such a way that it'll point directly east relative to the land, right? So let's do some relative motion. So we have our boat. Let's say this is our boat, right? We have a boat. We have one line, which is our boat speed, right? That's going to be 5 miles per hour, right? Or 5 meters per second. And then we have our river speed, which is going to be 4 meters per second. So we're trying to find what the magnitude of this is, right? We have it, so this is directly east. This is a right angle, right? This is pointing directly south, and our boat is pointing in an angle, so it's going directly east, right? So that means this is a Pythagorean triplet, right? 3, 4, 5. What's the missing number? 3. 3 meters per second. So our boat is moving 3 meters per second east relative to the land. Since the gap is 600 meters, that means that we know that time is equal to distance divided by speed, which equals 600 divided by 3, which equals 200 seconds, right? So the time that it takes for the boat to cross is going to be 200 seconds. It's moving 3 meters per second east relative to the land. Hopefully that makes sense. So that means that our answer is going to be that's the wrong tab. Our answer choice is going to be answer choice D, 200 seconds, right? All right, so we have 3 questions left. So a balloon is filled with helium gas. A balloon filled with helium gas is tied by a light string on the floor of a car. The car is sealed so that the motion of the car does not cause air from the outside to affect the balloon. If the car is traveling with constant speed along a circular path, in what direction will the balloon on the string lean towards? Okay, so this means that we're at constant speed, right? Constant speed. Let's go clear up. So let's clear all this. So we have a circle. We have a circle. That's the wrong color. We have a circle, right? We have a car, right? And it's moving at constant speed. So first thing we need to know, there's no net acceleration, right? There's no net acceleration, and our force, not no net acceleration. There's no acceleration, and our force, our external force is just going to be equal to 0, right? We're only going to have one acceleration here, and that's going to be our centripetal acceleration. That's keeping our car in this loop, right? Or else it's going to fly out. So our centripetal acceleration is pointed in this direction at v squared over r, which means our balloon is also going to lean towards the center of the circle, right? So that gives us our answer choice of D, right? All right, next. A sled loaded with children, starts from rest and slides down a snowy 25-degree incline, traveling 85 meters in 17 seconds. Ignoring air resistance, what is the coefficient of kinetic friction between the sled and the slope? All right, so this is a box on an inclined plane problem. Hopefully the kids aren't in the box, but let's do this, right? So we have our slope. We have our slope. We have our slope. We have our slope, right? We have our slope, and we have a sled with a lot of children who are in their impending doom. Now, one of the things that a lot of people told me while we were doing this was, we don't have a mass. What are we supposed to do? Well, you'll find out in a moment, because we don't even need mass at the end. So this travels 85 meters in 17 seconds, right? So our position is equal to 1 over 2 at squared, right? We have no initial position. We're assuming that we have no initial position, and we have no initial velocity, right? We start from rest and we go down. So 1 over 2 at squared. So x is going to be equal to 85, t is equal to 17. So this is 1 over 2 times a times 17 squared, right? I'm pretty sure a is equal to 0.588 meters per second squared, right? Okay, so that's our first part. A is equal to 0.588 meters per second. That's our acceleration. That's the first part covered. Next, let's zoom this down a little bit. So we know that our acceleration is that. So our force is going to be equal to mass times acceleration, right? Our net force is equal to our mass times our net acceleration. So what is our net force? Let's think about the components again. We have what components are going to affect this. First, we're going to have mg sine theta pulling in this direction, right? Next, we said that there's kinetic friction, right? This is moving, so we're going to have a kinetic friction of mu kn, right? Our normal force is going to be mg cosine theta. So that means that our net force is equal to mg sine theta minus mu k mg cosine theta, right? This is our normal force, right? In this direction, this is mg cosine theta. Okay, so now we can set these two equal to each other, and now you can already see why we don't need our mass. So ma is equal to mg sine theta minus mu k mg cosine theta, right? Cross out all these m's. We have 0.588 is equal to 10 times sine of 25 minus mu k of cosine 25. Now at this point, we can divide by 10, we can swap these around and do a little bit more, right? So we can do 0.0588 so sine 25 is equal to sine 25 degrees minus 0.0588 divided by cosine of 25 is equal to mu of k, right? And we can plug this in. Let me do this actually. Sine 25 minus 0.0588 divided by cosine of 25. And I'm gonna get 0.401, which is going to be this b, right? Another thing we can do, that just revealed everything again. Another thing we can do, we can just get to this spot and we can just plug in, right? We can just plug in, we have an equation, we can just see which answer choice fits, right? And that just saves a little bit of time, unless it doesn't, in which boo-hoo. But we just established that this is going to be equal to b, right? Answer choice b, 0.4. Now, final question. A 22 kilogram suitcase is dragged in a straight line at a constant speed of 1.1 meters per second across a level airport floor by a student on the way The individual pulls with 100 newtons of force along a handle that makes an upward angle of 30 degrees with respect to the horizontal. What is the coefficient of kinetic friction between the suitcase and the floor? Now this was quite interesting. So I'm gonna see if I can just do this, and pretend everything is fine. Alright, okay, so we've gotten here. So, first of all, we have a suitcase, right? We have a suitcase on wheels, on a level floor, and we're pulling it by the handle. This is 22 kilograms. Pulling it by the handle with a force of 100 newtons at a 30, this doesn't look like 30 degree angle, right? And we're trying to find, and the thing is, we're at constant speed. Acceleration is equal to 0, right? Our total, our sum of all forces is also going to be equal to 0. We're trying to find the kinetic friction, right? So, our constant of kinetic friction, right? Okay, so, first, we have a force, right? We have a force in this direction. We can split it into two components, right? We have 100 cosine 30, right? That's our horizontal component. And we have our vertical component, which is 100 sine 30, right? Okay, so this is going to be a force. We have a total gravitational force of 220 newtons, right? We have an upwards force of 100 sine 30, and we also have a normal force. Now, normal force, you might just say, oh, it's just 220 newtons, right? Wrong. This is going to be equal to 220 minus 100 sine 30, right? Think about it. If we have more force up than we have down, then this is just going to start floating up, right? It's going to start accelerating up. We're not doing that, so these have to perfectly cancel each other out. So our normal force is this, right? That means that our mu, right? Our mu kn is going to, our friction force is going to be equal to mu k times 200 minus 100 sine 30, right? And sine 30, yeah, sine 30 is just 1 over 2. So we can just say this is 50. So our frictional force is equal to 150 mu k, right? Okay, we have that established. I'm gonna make this a little bit smaller, just for, just so my head can be a little bit clearer. All right, so we've gotten to this point. We know that that's our frictional force, right? So our frictional force needs to directly completely counteract this 100 cosine 30, right? Because we have no net acceleration, which means that all our forces have to cancel. And that means that our frictional force has to be equal to our this force, right? This F of x. So that means 150 mu k is equal to 100 cosine 30, right? Divide 150 on both sides. We're going to get 2 cosine 30 divided by 3, which is equal to 0.577. Oh no. Oh good god. What have I done? What did I do wrong? Oh, I'm stupid. Okay, this is the why did I do 200? That's 220. Okay, so so that means that we have 100. Okay, that definitely confused a lot of people. So that's 170 mu k. So this is 170 mu k is equal to 100 cosine 30. So we can have 100 cosine 30 divided by 170. And that's going to give us around 0.509. Oh shoot, I wasn't even on that slide. So, slide 220 minus 50, that's 170 mu k. And then that means 170 mu k is equal to 100 cosine 30. So we just divide by 170 on both sides, and that gives us around 0.509, which is going to be our answer choice C. And with that, that's going to end off the second lecture for 2023 and 2024 for the FMA Club. I hate calling these a lecture. I'm just going to call them club meetings. So that's the worksheet answers. That's also the lesson. Thank you so much for listening. I'm sorry that some of it was a little bit messy, a little bit improvised. If you want some more questions, if you want to look back at some of the old stuff, you can go back to the 2022-2023 playlist. You can find that under the channel. And yeah, that's about it. Thank you so much for participating, and hope to see you next week. See ya.